My name is McCulloch, and we're starting a brand new institute on carbon and energy reduction in transport, together with David Bannister, who's over there from the Transport Studies Unit, and Colin Axon from engineering as well. Just to give a brief idea of what some of the issues are, is we luckily saw the increase in CO2 in the atmosphere from our previous speakers. That was a nice segue into this talk. This is the consumption of energy from the BP Statistical Energy Review 2008. It just shows you what the growth in energy over the last 20 or so years has been. What's been interesting is that from about 2003, 2004, there's been a tremendous increase in energy consumption. And a large amount of that has also been from oil consumption, and oil is one of the primary energy vectors that goes into the transport industry. So if we are going to be able to reduce the amount of carbon dioxide over the next 20 or 30 years, one of the key areas is to try and reduce that segment of that, and that means reducing the carbon in transport. So just to clarify a little bit of chemistry in there, one of the main constituents in petrol, which is of course being distilled out of the oil that we mentioned earlier, one of the main constituents is octane, and shows you what happens when you burn octane, which is your C8H6H18 with your oxygen. You then produce carbon dioxide. The interesting numbers here is that 228 grams of petrol or of octane will produce 704 grams of CO2. So that means that you get a substantial increase in the amount of CO2 produced because of the carbon from the original petrol there. And that is basically because of the weight of the oxygen that's in there. And that ties in to say that basically for every liter of petrol that's burnt completely, you get approximately 2.3 kilograms of carbon dioxide. Okay, so that means for every liter, you're producing about 2.5 kilograms of CO2. What this translates to is in vehicles at the moment, that means for approximately every 100 kilometers traveled, you're going to be producing about 13 kilograms of carbon dioxide. So that means one of the things that we want to be able to do is to reduce that number there, the number of kilograms of carbon dioxide we produce for every kilometer traveled. However, we've got additional challenges on top of that normal scenario. One is that we know we've got an increasing population, and the latest estimates, as we all know, is going up to about 9 billion people. The problem with that we have is that that segment of the population is growing richer as well, and therefore the expectations are growing. So whereas one traditionally has this form of transport in the developing countries, that's going to be replaced by vehicles. So that means that the carbon dioxide production is going to be larger. Also, we're finding there's a growth in the distances that people are commuting over time, especially with the impact of urbanization. And these three, together with our desire to go to 20% carbon dioxide, means that we need at least a factor of 15 decrease in the amount of carbon dioxide per kilometer traveled. Is rather a large number. Put another way, it means we need to use 7% of the carbon dioxide than we do presently per kilometer traveled. Question, can it be done? Well, in our lab, we've already developed a vehicle which will do 5,500 miles per gallon, okay, which comes down to approximately 132 grams of carbon per 100 kilometer. Okay, so that's a factor 100. So things looking good. The only problem is that's what it looks like. Okay? So the question is, it shows that the technology is capable to drive us. And the importance of this project is it shows what is the envelope to which we can work to. So it shows that there is hope. Okay? Something that's a bit more medium term is these are two vehicles which have been released this year. Okay? We were involved with the top one. That is a car that we developed together with Morgan. It's a hydrogen-based sports car. Sporty handling, in other words, it'll do 0 to 62 miles an hour, which is 100 kilometers an hour in about 6 or 7 seconds. It will have a range of about 250 miles on a single charge. And what's interesting, it's using a combination of a hydrogen fuel cell together with ultracapacitors. The hydrogen gives us the range, but the interesting thing with this one is it's only a 20 kilowatt fuel cell. To give you an idea, that's about 1/3 of the power that we'd normally find in a VW Polo. Okay? And yet we can still do 0 to 60 in 6 seconds. The reason for that is because we've combined that technology with ultracapacitor technology, which allows you to have a really rapid dump of power. so we can get the really sporty performance. It also means that when we brake, the energy doesn't go into heating up the brakes, it actually gets recovered, so we can use it for the next acceleration cycle. This is the Lightning that was just been was released about a couple of weeks ago at the London Motor Show. What's interesting with that, that's a purely battery vehicle, but they're using batteries there where we can charge up the batteries in about 4 minutes. So things are really moving fast in that area. A year ago, you'd be looking at a half-hour charge time. So battery technology is moving quite well. It can do, the Morgan sports car can do about 150 miles per gallon. So that starts to show you where we're starting to push the boundary. So we can see that the technology is pushing the boundaries. We can see that we can do 5,500, but we can see with these two vehicles that we can do that in a form which is actually acceptable to most consumers. I'm sure not many people will object to having one of those. So the approach to the Institute is basically to say we need to be able to integrate both the technology pushes and the economic pushes and to be able to model that so that we can understand how the overall transport system can migrate from a system of, where we can push to getting a factor 15 decrease in carbon dioxide. In order to do that, we'll be looking at all of the primary energy sources and looking at how they migrate through the energy vectors being hydrogen, electricity, maybe ammonia or other versions, and looking at how those all interact with the vehicle technology themselves. So that by looking at understanding that whole system, we can then really start to understand what is the true resource to function, what used to be called well-to-wheel efficiency. So saying, given that amount of resource, how far can we actually travel? We've already got a visiting prof who's working here, is looking at the same issues, but in marine environment, because we think marine transport is actually a substantial area that needs to be addressed as well. So our objective is that by the time we complete our 3 years, in 3 years' time, that we will have a suite of credible modeling tools which will be able to provide the analysis so that we can understand what are the right policies to drive this forward. And through that to identify what is the correct roadmap that not only the UK but the world should follow for a low carbon transport. Thank you very much.